Pretty large chapters in this course. So we're looking at Laplace transforms, and lately we've been looking at how they are used to solve differential equations. So the actual solution method. The Laplace transform, remember, is this device. It's an integral transform. You stick a function of t in, and what pops out the other end is, where's it gone? This up, you stick a function of t into it, you integrate it, you integrate t out with this extra factor, this exponential factor, which depends on this new variable s. So the transform, the value of this thing here, the value of this integral is a function then, function of the new variable s. We looked at some initial examples, and crucially, we looked at important properties that it had. You've got various library of functions here, library of standard functions in the table of transforms down the left, standard functions down the left, and their transforms down the right, which we make use of. But crucially, we started looking at important properties of the transform. This lies behind why they provide a method for solving the ODEs. Key properties are, the first one, the most straightforward one to achieve or to prove, is that the transform is linear. You take a transform of any linear combination of functions, the value is the same linear combination of the individual transforms. Okay. A theme you've seen come up again and again. Your study of linear transformations with Stephen, your study of the properties of differentiation. Differentiation is linear. The other crucial property was theorem 2.3, the transform of derivatives. We're faced with an ODE at the beginning of the thing. The ODE features one or more unknown functions in it we're trying to solve for. What this property says is, okay, we may not know what x is, but we do know that there's always a strong relationship between the transform of the derivative of x and the transform of x. Okay? So it's not that we know the transform of x here. It's still something, when we use it, it's still something unknown, because when we start trying to solve the equation, we don't know what x is. But we do know this, that there's an exact strong relationship between the transform of a derivative and the transform of the undifferentiated function. Okay? And there are versions of this. This can be extended to the higher order derivatives as well, to the second and third, and any derivative of x. Its Laplace transform fundamentally only relies on the transform of x, the original function x, and the polynomial in S, and the coefficients of the polynomial, these x subscript i's, these are the various initial values of the various intermediary derivatives of x. The original function x itself, that would be x subscript 0 in this notation, the undifferentiated function. And this is the formula for the nth derivative. So this polynomial in S, this part, features the initial values of all the earlier derivatives of f, between 0 and up to n minus 1, the n minus 1th derivative. This led us to, so just finishing the summary of previous stuff, this led us to this four-step method for solving the differential equations. Now this is crucial part of this course. It's a crucial ability we want you to have. So we're going to see some more examples of it today. We're going to extend it slightly to look at simultaneous systems of ODEs, pairs of ODEs, but that's still going to emphasize the same techniques, the same basic steps involved in solving such a thing. So just to summarize, the four main steps was, first of all, to take the Laplace transform of the whole equation, the whole ODE. So transform of the left-hand side equals the transform of the right-hand side. You applying those two key properties as you do it, the linearity of the transform and the property that relates the transforms of the individual derivatives, relates them all to the transform of the unknown function y. So what you end up getting is converting the differential equation to an algebraic type equation, but now still with an unknown quantity, which is the Laplace transform of y. But the algebraic equation is kind of easier to solve. And after you insert any supplied initial conditions, you then solve the transformed equation, and you end up with a solution for y bar. So y bar there is indicating the Laplace transform of y. You end up with a description for y bar as some kind of function of s. Okay? And then in principle, there's only one more step to do, is you take the inverse transform. That function of s that you found, you take its inverse transform. And that will give you the original function y of t, the solution to the ODE. Okay. Now, yeah, let's continue. So we're about to look at section 2.4, which is on simultaneous coupled ODEs. And the example or examples we're going to start looking through will show us more of these steps in operation and getting some practice with it. But any queries on the top level kind of description of it or on that overview? Is that okay? Okay. So just one little thing to look at. So if you missed the last couple of sessions, you look at the last couple of lectures, we did examples of these things. Or if you look at the last lecture last week, we did examples of applying this method to solve differential equations. Example 2.8 illustrates a common technique that's needed at the end. So just before we perform step 4, we reach the end of step 3, which maybe typically throws up an example like this. You end up solving the transformed equation. Maybe you might get something like this, that the transform of y bar is this function of s. So that's great. You've solved the transform problem. Now you just need to find the inverse transform of this function here, and you'll have your solution y of t. Our main tool for finding the inverse transform is working with the table of Laplace transform. Okay, those are 2 pages here in the notes that are taken from the formula handbook, which you'll have at your disposal during the exams. Now the problem is when you look down that table, you don't see any functions looking exactly with that exact pattern. So how do you proceed? Well, we always have tools of using some kind of partial fraction expansion or some kind of algebraic rewriting of this so that it looks like functions on the table. Now, the thing that you notice about here is if you start thinking about doing a partial fraction expansion, you'll notice here that this thing is already as simple as you're going to get. Okay? You can't factorize this denominator into simpler polynomials with real coefficients because it's an irreducible polynomial. It's got a negative discriminant. Number theory students, we were discussing discriminants this morning, but this polynomial is a negative discriminant. You can't factorize it any further. And so you're looking on your table of transforms for functions that have a quadratic denominator. If you flick back to the table and look for these functions, you start to see them in the bottom half of that first page. Various functions here with quadratic denominators. Now, our polynomial in that example, it had an s term. So it's not going to be any of these which feature quadratics which don't have an s term, just an s squared term. It's going to be one of these, okay? So these functions here have quadratic denominators which still have an s term, because when you square this bracket, you'll get an s term out. But the polynomial is presented in this completing the square way, the square of a linear factor plus a correction plus an extra constant term. And then you've got various numerators, either the quantity s, the quantity omega, quantity s plus a, or the quantity omega again. And various combinations of plus or minus on the denominator paired with those numerators. So coming back to this example here, before we go to the simultaneous systems, this one here, example 2.8, the bottom of page, bottom of page 49. So you can see what goes on here, okay? The appropriate form for the denominator is going to be the square of s plus 2 plus 9. That's what you get when you complete the square on this polynomial here. So we already recognize that we're talking about an s plus a with a equals 2 and a plus omega squared with omega equals 3. But then you got to look at that numerator, 3s plus 18, and you got to see, well, how can you break that down? So it's either in the form s plus a, which was one choice of the numerator from the table, or with the constant omega. So that was the other option from the table. Yeah, there were two entries with polynomials like this. One with s plus a in the numerator, the other one with omega. So you got to work on your numerator of 3s plus 18, break it down into what kind of combination of s plus 2 and the constant 3 you need in order to equal 3s plus 18. Well, we've got 3s here, so it's going to have to be 3 times s plus 2 to generate the 3s. The 3 times 2 generates a 6. So there's a, what, there's a 12 missing. There's a 12 missing, so that's going to be generated by 4 times 3. So the appropriate combination is 3 times the s plus 2 fraction plus 4 times the 3 fraction. Okay. And now what we're looking at is a linear combination, constants 3 and 4, constant coefficients 3 and 4, a linear combination of these two functions. These two functions are on the table of Laplace transforms, so we can read off their inverse transform. First one inverts to a exponential times a cosine. The second one inverts to an exponential times a sine. You can read off the inverse transform, and we're thinking of this as something appearing at the end of solving an ODE. So we read off the solution to the original ODE. Okay. So before doing step 4, before carrying out the inverse transform, we'll often need either this kind of re-expressing, rescaling kind of process, and very often we'll need partial fraction expansions as well. Okay. This thing is already as simple as you're going to get it in a partial fractions form. It won't go any simpler. It won't go as a combination of simpler ones. So we introduced this kind of rescaling and re-expressing as an appropriate linear combination of functions from the table. So, okay, any questions about that aspect of it? Okay, let's start working through some more examples here. So I'll switch to the overhead. So we come across section 2.4, which is the top of page 50 here, and these are called, well, this is a pair of simultaneous ODEs. So there's nothing more we need. We already really have all the tools that can deal with a simultaneous pair of differential equations. Now, the term coupled is sometimes used for these. So what we're talking about here is there are now two unknown functions, an x and y function, two unknown functions of time t, that their properties are described by this pair of differential equations. Okay, so we're looking for a pair of functions that simultaneously solves both of these equations. Now, you'll notice that there isn't just one equation for x and one equation for y. Both equations feature x and y mixed up together, x and y and their various derivatives. So this is the property of coupled ODEs. So coupled ODEs refer to the fact where you've got a set of differential equations. The unknown functions are all tangled up in all the equations. So you can't consider the different equations as single problems on their own, because the various variables, the various unknown quantities are tangled up together. So it's not as if we're going to solve the first one and find x and solve the second one and find y. That can't be done, because x and y are mentioned in both. So they're coupled together. They're mixed up or coupled together. Okay, but in principle, we just go ahead with our same 4-step process, okay, and see what we can do. Okay. So let's just dive into it, and we'll describe what we're doing as we go. And I'll re-emphasize, as we go through the solution here, the various parts of the 4-step process. Okay. So let's just put down in slightly more compact notation. So solve for functions x and y. We're going to solve these two systems. So, and I'll use the dot notation for derivatives. So you're familiar with this notation. Z dot refers to the first derivative of z. Z double dot refers to the second derivative of z. As you could appreciate, it's a lot easier to write z dot or z double dot to refer to these. It takes less ink. And it all fits on one line. So we got x dot plus 4y dot plus 5x equals 3. Our second equation is y dot plus 3x plus y equals 2t. Remember, the constant term, if you like, from the differential equation, the one not involving x or y or its derivatives, we're allowed to have functions of the fundamental independent variable t there as well. So that's what we're facing at the beginning. We are given initial conditions. These are first order differential equations, so they will likely only depend on the initial values of the functions themselves. So we got two initial values, y of 0 is 2, and x of 0 is -3. So step one is always to transform, well, it was to transform the equation, so we simply now transform both equations. We're going to take the Laplace transform of both equations. Now there's two variables, x and y, that are unknown, these two functions. So we're going to write, going to keep the notation, we'll write x for the Laplace transform of the function x of t, and, sorry, x bar, and y bar for the transform of y of t. Just this compact notation, which is good to use when you're going to be doing lots of equations mentioning these quantities. We don't want to be having to write curly L, curly brackets all the time. So just x bar and y bar. But okay, so while we're doing the transform, I want to simultaneously, I don't want to write down loads of individual steps. I want to simultaneously, I want to apply the linearity. So when I take the Laplace transform of the left-hand sides, it'll be the transform of the first bit plus the transform of the second bit plus the transform of the third. So I'm applying linearity as I go. And what are the bits? Well, the bits are either x or y. Well, I've already know what I'm going to write for that, x bar and y bar. Or they're the derivatives. And for the derivatives, I'm going to call upon the transform of derivatives property, which tells me what the transform of x dot is in terms of x bar and what the transform of y dot is in terms of y bar. So transform both equations. Using linearity principle and the transform of derivatives property. It's good to indicate the properties that you're using, the justification for the steps you're making. Okay, so x dot transforms to s times x bar minus x of 0. That's the transform of derivatives property for a first derivative. Transform is the s times the transform of the undifferentiated function minus the initial value. Y dot transforms to 4 times s y bar minus y of 0. Okay. I'm using linearity. I'm transforming each of the 3 terms individually and adding them together. And 5x, well, that transforms to 5x bar. The right-hand side is the constant 3. Constant 1 transforms to 1 over s. So by linearity, the constant 3 transforms to 3 over s. So that was a lookup from the table of transformations to get transform of 3. Okay, it's the first equation. The second equation would be similar kind of thing. sy bar minus y of 0 plus 3 times x bar minus x of 0 plus just y bar. And the transform of 2 times t, well, you look up on the table, the transform of t is 1 over s squared. By linearity with an extra factor of 2 there, it's going to be 2 over s squared. Is everybody okay just with going to there? These are all instances of the transform of derivatives property, which is on the table, summarized on the table, but is the result theorem 2.3. Sorry, theorem 2.3. They're all various instances of this. Oh, okay. Transform of a first derivative is s times transform of the undifferentiated function minus the initial value. Okay, so that's all. That's being used in 1, 2, those 4 places. Yeah. Yes, any other questions?
Sorry, in the second equation, for 3x, should that not just be 3x bar?
3. Oh, sorry, crikey. Yeah. So it wasn't an x dot, it was just a, thank you, correction. Is that the other comment there? Yeah. Anything else? Thank you for the tut. Okay, so yeah, so that was just x on its own, so it just transformed to x bar. Okay, now you see we've got these constants here, x of 0, y of 0. Now they were supplied to us. Okay, so we'll put in the initial conditions, put in the supplied initial conditions, and we'll tidy up a bit. We still got the first equation. So x bar, well, how many x bars do we have? We've got, in total, we've got s plus, oh, that's a bit crazy, s plus 5. So you'll have to distinguish your s's and 5s. We've got s plus 5 x bar. Let's look at our y bars. We've just got 4s y bar. And the constant term, well, we've got a minus 3. So we've got a 3 and 4 times minus y0. So we got a minus 8. Great. 3 and a minus 8. 3 minus 8 is minus 5. Is that correct? And that's still equal to 3 over s. So just putting in the initial conditions, tidying up. Many x bars? We've got 3 x bar. S bars, we've y bars, we've got s plus 1. Constants, we've got minus 2, just minus 2. And that's still equal to 2 over s squared. Okay? So these are our transformed equations. They are structurally, conceptually, they are simpler, I think, than the original pair of ODEs. In the original pair of ODEs, we had the two unknown quantities x and y and their derivatives. And there's no immediate, easy way to reconcile a function and its derivative. They can have all sorts of, different behavior. Whereas in this system here now, there's just two unknown quantities, x bar and y bar. They are understood to be functions of s. And the various coefficients are constants and s. And if it was higher ordered, there might be an s squareds or s cubes in there. This is just first order, so we just have some s's already. We've got an s squared over here. So now what we've got is this simultaneous pair of algebraic equations, okay, which we now want to solve. Okay, but there are two quantities to solve for, x bar and y bar. So we now go for solving these and somehow finding x bar of s equals some kind of function of s, and y bar of s equals some kind of function of s. That's what we're going for. Okay. Maybe let's make it, before we do that, let's get those constants over to the other side. Maybe simplify things a little bit, because things are going to get a little bit involved in a moment. So I want to take that minus 5, put it over here as a plus 5, and I just want to keep things compact. So it's going to be 3 plus 5s. Keep it as a single fraction. And down here we've got 3x bar plus s plus 1y bar. Put the 2 over the other side. And it's going to become 2s squared if I want to put it over the denominator. S squared. Really, let's keep labeling these as 1 and 2. They really still are first and second transformed equations. Okay. So now we want to go for solving them. And I mean, how do you solve simultaneous equations? Fundamental principle is you want to reduce the number of variables. Do something to the equations that eliminates one of the variables so that you can home in on one of them. Okay. So we got to do something to these to isolate one of the variables. So how about we cancel the x bars? Get rid of the x bars, so we're just left with y bars. We're just left with an equation which only features y bar, and then we can see what its solution is. So how do you cancel the x bars? Well, you want to take some kind of combination of the two functions, such that some kind of combination of the two equations, such that when you add the two equations together, the x bars disappear. See, they've got different coefficients. One is the coefficient s plus 5, the other one is the coefficient 3. You got to cross multiply in a way. You got to look at 3 times equation 1 minus s plus 5 times equation 2, don't we? If we look at that combination of equations, then the x bars will no longer be there, because we'll have 3s plus 5 minus s plus 5 times 3 times x bars. So there won't actually be any x bars. So we'll call this equation 3. So equation 3 is, well, there's no x bars, and I have 12s y bar minus s plus 5 s plus 1 y bar. Now the right-hand side is going to be a bit hairy. You have 3 times the right-hand side of 1, which is 9 plus 15s over s, minus s plus 5 times the right-hand side from equation 2, which is 2 plus 2s squared, all of it over s squared. Agreed? Yes, Killian is the correct answer. Okay. You see the utility of what we've done. We've gotten rid of the x bars. Okay. We've got some work to do on tidying this equation and working with it, but in principle, this is going to allow us to find the solution to y bar. Okay. Just got to tidy it up, make y bar the subject of the equation. So let's do that. So what have we got on the left-hand side? Well, on the left-hand side, so this is equivalent to, on the left-hand side, multiplying y bar, we've just got a big polynomial in S, don't we? Some s squared, some s's, some constants, some s's. So it's just a big polynomial in s squared. So let's look at the polynomial that it is. It's so you've got minus s squared. Well, we like to write our polynomials with positive s squared in them, so I'm going to stick a minus sign on the outside. You got s squared minus. How many s's do you have? Well, here you've got 5s, 1s, you got 6s. We got minus 6s plus 12s. So in total, there's 6s. But if I'm putting a minus sign out there, I got to make it minus 6s inside. And the constant term comes from 5 times 1, which is 5. It's got a minus sign. So it's a constant term of minus 5. I've already got a minus sign on the outside, so it's a plus 5. Plus 5 on the inside. Agreed? Over on the right-hand side, well, this thing is just some humongous, well, it's just something over s squared. Agreed?
Yeah.
Yes. And what's on the top? The top Well, this is going to be that's a cubic in S. I'm going to have to multiply that by S, so quadratic in S. So in total, there's just a cubic in S on the top. You subtract these functions. So let's just look at what we got. So the cubes come from here. S times 2S squared. It's 2S cubed. It's got a minus sign. So it's minus 2S cubed. The S squareds, you're going to end up with 15S squared from here. You get 10, minus 10 there, and 2. It's minus 12 plus 15. No?
No. It's 2S, not 2S squared.
No, sorry. I'm looking for S squared. So
Yeah. So you
15 minus 10.
15 minus 10. Yeah, 5 times 2S squared. It's 10S squared minus 10S squared, 15. So plus 5S squared. And then just S's and constants. The S's, minus 2S here. And that's going to be multiplied by S to get it over S squared, so 9S. So 9S minus 2S, 7S. Constant term is just your 2 times 5, minus 10. Yeah. Okay? Everybody okay with it up to there? Okay, but we're zeroing in on our solution y bar. Remember, y bar is a function of S. So now we just got to divide both sides by that polynomial. We notice a couple of things. Well, firstly, this polynomial here on the left, it's S minus 5 by S minus 1, isn't it? Factorizes. So we're going to divide both sides by that. So the new denominator here is S squared, S minus 5, S minus 1. I want to avoid superfluous negative signs, so I don't really want to stick a negative sign in the denominator. It looks a bit ugly. But if I did introduce a negative sign there, I could compensate for it by, it's a factor of minus 1, just applying that factor of minus 1 to the top. So I can just simply flip all the signs there. And that fixes it up, makes it look a bit nicer. 2S cubed minus 5S squared minus 7S plus 10. Okay? But divided both sides by minus S minus 5 times S minus 1, this quadratic. So put those in the denominator. Again, distinguish your S's and 5s. And that minus sign that would have appeared there, it's just a factor of minus 1. I just multiplied it through the top, flipping the signs. So it's not simplifying a bit as we go. Now, we got a cubic over a cubic. Sorry, cubic over a quartic, something to degree 4. It just might some of these factors simplify? Might some of these factors disappear and cancel with the top? Well, 0 is not a root at the top because it's got a constant term. Maybe 5, so looking at this factor, S minus 5, maybe 5 is a root in the top. I don't think it is because you get 5 cubed is 125, so you get 250 minus 5 times 25, 125. So 250 minus 125 leaves you with 125. 125 minus 35 plus 10. Well, that's still not 0. So 5 is not a root there. Well, actually, when you look at 1, the root 1, S equals 1, that is a root, isn't it? Because when you substitute in the value S equals 1, you're really just summing the coefficients. And 2 minus 5 is minus 3, minus 7 is minus 10, so plus 10 is 0. So actually, yeah, S equals 1 is a root to the numerator. So we can simplify the numerator by dividing out by the factor s minus 1. So we can simplify the denominator to s squared times s minus 5. And the numerator becomes the quotient that's left behind. Quickly, I've got to prepare it here. 2s squared minus 3s minus 10 is the polynomial that's left behind after you divide the cubic by s minus 1.
So you divide numerator and denominator both by s minus 1.
By s minus 1. So I can cancel that factor of s minus 1. So it's present in there because s equals 1 was a root of that, we noticed. And that's the other factor that's left behind. Okay, so now this is looking like something we ended up with at the end of step 3 before. We've got a solution for one of the unknown functions. So in principle, we're just going to take the inverse transform here to recover y of t. But we can't do it immediately because this is a complicated rational function. Something of this type exactly doesn't feature on the table. We've got to find its partial fraction expansion. So that we see it as a combination of simpler rational functions which are on the table. So we need the partial fraction expansion. Thankfully, the denominator is already simplified. So it's going to be an a over s plus a b over s squared plus a c over s minus 5. That's the kind of partial fraction expansion we need. Will you allow me to shortcut the finding of those coefficients? We know the process of finding partial fraction expansions. You got to collapse that together again. It's something over s squared times s minus 5. Look at what happens to the a, b, and c. They'll give you a quadratic with a, b, and c. Combinations of them in the coefficients. Get it into standard form. Compare it with this one. You get a system of equations for the a, b, and c. Should I go through it? Or? Yeah, I could go quickly through it. S squared s minus 5. So the a is going to multiply s times s minus 5. B is going to multiply s minus 5. And the c is going to multiply s squared. Agreed?
Is that as?
S minus 5, yeah. When I wrote it first, I forgot the s. So it's a times s minus 5, because you got to get that to the denominator. S squared times s minus 5. So getting that into standard form, well, it's just a quadratic in s squared. You got a plus c s squared. How many s's? You got minus 5a s's here, plus b. And where's the constant term? The constant term is just minus 5b. So actually this probably solves fairly quickly. The solution just unravels because, look, the constant term is minus 5b, so that's be minus 10. So by comparing the coefficients in these two numerator polynomials, the b has to be minus 2. Now b is 2. If b is 2, then minus 5a plus 2 must equal minus 3. A must equal 1. And if a is 1, then 1 plus c must equal 2, so c must be 1 as well. We could read off that solution starting with the constant coefficient, comparing minus 5b to minus 10. B has to be 2. Then you compare the s coefficient to the s coefficient, gives you a solution for a. Then you compare the s squared coefficient to 2. That gives you a solution for C. So y bar is 1 over s plus 2 over s squared plus 1 over s minus 5. This is good. These nice, simple, rational functions are all, well, either them or constant multiples of them are on the table. So we can apply step 4 now. So we can take inverse transforms. To get y of t is the inverse transform. Again, we're using linearity and reading entries off the table. So y of t is the constant 1 plus 2 times t plus the exponential e to the 5t, is it? E to the 5t. So that's our solution. There's our solution for y. Of course, it's only 1/2 of the solution to the original problem, of course. The original problem featured x as well. So we still need to find x. So in principle, we need to return to find x bar and then x. That's the general principle. Okay, we solved the simultaneous pair of transformed equation. We found the solution to y. Well, we found the solution to y bar first. In principle, we could go back to one of these two equations featuring x bar and y bar, substitute in our y bar, find the x bar, and invert it. Okay. However, slightly easier in this, slightly quicker in this example, is to examine the second of the original ODEs, which was y bar plus 3x plus y equals 2t. The second of the original ODEs. And you see, because we already know what y is, if we substitute in the value for y, that will tell us straight away what x is. The y bar is going to be the derivative of y, 2 plus 5e to the 5t, plus 3x plus y, which is all this again. It's equal to 2t. We'll just shove everything over the other side, and you'll get your solution for x of t. I'll just shortcut to that. Basically substituting y, the y that we found in here. So the x you get out is minus 1 minus 2e to the 5t. Just the second half of the solution to the original ODE. Again, you see no essential modifications to the solution method are needed to deal with coupled ODEs. Just exactly the same principles, just applied one after the other. Eliminate one of the variables, very familiar principle to you for solving systems of equations. Eliminate one of the variables, find the solution to the transformed functions, take it inverse transformed, and you get that original function t. And then go back and chase up the other functions as well. Okay, if it's a big coupled system featuring lots of functions, that could take a long time to do by hand. I'll show you next time the commands to, or you should look up yourself in the meantime, but I'll demonstrate to you next time MATLAB's capabilities to solve these symbolically as well. And look at the solutions. Okay, so is Callum here today? Where's Callum? Callum just has something crucially important to tell you. You should all listen.
Okay, hello. Now these assignments are pretty much done. I think people want a course night out. So I spoke to some people and came up with the idea to go to Font 2 weeks today, 12th February, have a few drinks, go to factory. Yeah. So I was hoping there'd be more people here today to tell them that.
I was too.
So if you just pass on to your friends that know lecturers have been invited. So good to see you. Be good.
Well, 9 p.m. is bedtime in my house, I tell you. 3 young kids. But anyway, what was the time, sir? Font,
9 o'clock onwards.
what date?
12th February.
12th of February.
9 p.m.
Yeah. And then I'd suggest get to factory before 12 because it's like cheaper entries. Yeah.
Factory, what's factory? Where's factory?
No, the one just at the road.
Which one? The one by the bridge, by the train station. So the nearby font.
Factory is nearby farm.
Yeah, it's like over the road.
So you want to meet in front first and then go to factory for drink.
No.
I'll meet the font and then go to the nightclub.
No, factory's a nightclub.
Oh, okay.
At midnight.
At midnight.
I'll be getting up by then for the next day.
Is it Friday?
Okay, thanks, Callum.
Is it Friday?